Welcome to ECE 442-542. We have basically a pizza party going on as we are trying to review for exam number 2. You'll maybe be in a good mood relative to trying to go over what we're talking about, and hopefully you can eat and listen and observe what we're talking about. The process hasn't changed from the previous lecture. 2 sheets of notes, a Ztransform table, and the typical nose. And for reviewing for exam number 2, you should focus on homework number 3, and which talks about region of convergence and the inverse Ztransform. Homework number 4, which is discrete equivalents. You should be comfortable with those particular problems on that, and I would also recommend that you look at the practice exams that are available on the D2L website. To go through some of these topics, let me just scroll through these, and maybe you won't need to write them down, but I want you to start processing what it is that we're talking about, and I may have to back out a little bit more on this particular graphic. Here is our generic description of the Ztransform as this infinite sum involving potentially sequences at negative time indices and sequences at positive time indices. And what I'm trying to illustrate is the connection between when a sequence is defined and the corresponding region of convergence. Maybe, I'm not sure I'm going to fit all of these on the same screen, but I hope that you can see that if you have a disk region of convergence, that's this inner circle inside all of your poles, then you have a non-causal, and that corresponds to values of x that have a negative time index. And if you looked at what would happen if you picked any point inside the blue shaded area, which is, let's say, z equal to 0, and you plug that into this x at time 1, you can see now that you're dividing by 0, and that makes no sense if this is a well-behaved or a bounded expression for capital X of z. Which means then that all of these time values of x for x equal 0, for n equals 0, n equal 1, n equal 2, they have to be 0. That's why we have a non-causal waveform when we have a region of convergence that's a disk. That's independent of whether we have a bounded or an unbounded behavior. What we're saying is just when is this waveform defined? We could also look at this region of convergence that's beyond all of our poles, or its unbounded region of convergence. In that case, we have a causal waveform, and if we have an annular or bagel shape, with some poles interior to the region of convergence and some poles exterior, then we have a two-sided waveform. And then we have what I'm trying to illustrate diagrammatically. We have all possible index values of x that are available to us. Meaning, with just this one plot, or this one diagram or figure, you should, I hope, be able to make sense of the connection between a region of convergence and which particular indices x is defined for. Is that clear? So if you want to know, based on a region of convergence, where n is, or what x of n is defined for particular values of n, hopefully this picture will help you make that connection. The top two, you have a one-sided, either interior or unbounded, And in the bottom, you have a two-sided, and now you have this annular ring. As I said before, that differs, or that does not tell you whether or not you have a bounded or an unbounded response for those X events. Let's look at some possibilities. For example, if we have a non-negative time indices, what's that referring to in terms of causal, non-causal, two-sided? What do we have if we have a non-negative time indice option for our time sequence X event? Is that two-sided? Is it one-sided? If it's one-sided, is it causal or non-causal? So this is actually now a causal sequence. Or N is non-negative. Now, that means that what's our region of convergence? It's unbounded, isn't it? It's beyond all of our poles. That's now what we have, but now we could have two different scenarios. Suppose that all of our, or a mode relative to that region of convergence, suppose that the biggest pole is still bounded below 1 or less than 1. With n greater than or equal to 0, do we have an unbounded or a bounded response? If r is less than 1 and we have a causal sequence. So now we have r raised to higher and higher powers of n, where n is positive. So r, if it's less than 1, now we have, let's just pick one, 0.8, 0.8 squared, 0.8 cubed. That's just shrinking, so that's giving us a bounded response. And if you think about that, if the biggest pole is still inside 1 in terms of a radius, and the region of convergence is beyond that, then the region of convergence contains the unit circle, which is also another way of thinking about, is my response bounded or not? Contrast that with having a mode that's bigger than 1. So now you have a pole, let's say at 2. The region of convergence is still beyond that pole, so you have a causal sequence. But now what kind of a response? And now it sort of should be clear that this is going to be, if you have 2 and raise it squared, cube it, this is going to give you an unbounded response. What about if we had negative time indices? Do you see the region of convergence? And if you don't, you have it available to you if you just have that previous image or picture or diagram in play. If you now have negative time indices when you have a sequence defined, that's now going to be a non-causal and now we can ask the same kind of questions. If we now have negative time indices and all of our modes are inside 1, is that giving us an unbounded response or a bounded response? If all of our modes are inside of 1 in magnitude, and we have a non-causal sequence, what kind of behavior do we have in that sequence as a function of time? That's unbounded, isn't it? Because if we have a non-causal sequence, our region of convergence is interior to all of our poles, and we now have a pole that's inside 1, so this is going to be an unbounded response. Or we have 1/2 raised to a -1, 1/2 raised to a -2. So it's really 2 squared, 2 cubed. It's growing unbounded in a negative time index way. If we now have all of our poles bounded outside 1, and we have a region of convergence that is the disk that includes the origin, we have a non-causal, it should be clear now that we have a bounded response. And you should be able to very quickly sort of go through that logic. What's my region of convergence? Oh, that tells me whether it's causal, non-causal, or two-sided. And now let me focus on where my poles are relative to that region of convergence and where are they relative to the unit circle. In the last case, if all of the poles are outside of 1 and we have a region of convergence inside all of the poles, that region of convergence does include the unit circle, which is another way of concluding this bounded response. What about inverse Z-transforming? This we have to have not only the transform, but also the region of convergence in order to uniquely identify the sequence y of n from a Z-transform capital Y of Z. Just by looking at the denominator roots, we can tell what kind of structure we are going to have in our time domain. And we can have a combination. If we have real poles, then those are going to be exponential. If we have complex poles, those will be exponentially damped sines and cosines. And in general, if we have complex, then we're going to have an exponentially damped cosine and an exponentially damped sine of the same angle or frequency, and we'll just have to figure out how much of each of those sine and cosines we have. Let's work through some of those. Suppose I give you this, y of z. The very first thing you probably want to do is pull out your calculator or the quadratic formula and start finding, are my roots, and I will probably on the exam give you a factored form where they may be quadratic, but I may not factor it beyond that. But if I give you a combination of quadratic factors, you need to factor each of those quadratics and determine, are they real roots for that each of those quadratics, or are they complex? Yes. So if you find the roots on the calculator, just say from calculator and give me the roots. That's fine. But in this case, we found the roots, and hopefully it's clear that if I had a product of 0.5 and 0.25, I end up with half of a quarter, which is 0.125 or 1/8. That's my constant, and the sum of 0.5 and 0.25 is 0.75, and that's my coefficient that's scaling my linear factor. So I now have two real poles for y of z, and you should immediately know what the structure is in the time domain. And what's my region of convergence tell me? What kind of a sequence? Is it two-sided? Is it one-sided? If it's one-sided, is it causal or non-causal? Could I have a region of convergence that said the magnitude of z is greater than 1/4? Why can I not have that? Because you cannot have poles inside the region of convergence. So now this one says, oh, the region of convergence is beyond every pole in your transfer function or in your transform. And now what's that say? One-sided or two-sided? One-sided. What kind of behavior? Now it's either causal or non-causal. Now you just pick a point in your region of convergence and substitute it into that infinite summation sequence and say, which one do I have? Well, this should, since it's an unbounded, this gives you a causal behavior. And now you have causal behavior with a region of convergence that goes outside from z equal to 1/2, so it includes the unit circle, you should now be able to conclude, oh, I know that I have 1/2 to the n plus 1/4 to the n with some scaling if I don't do the partial fraction expansion. I know it's n greater than or equal to 0, and I know it's bounded, because these are all poles inside the unit circle. If you actually did the partial fraction expansion, in order to preserve that z in the numerator, we've learned the strategy of dividing the original transform by z. So now we have y of z over z. We find the partial fraction expansion coefficients from that, and then we multiply everything through by z to give us our capital Y of z expression. So that now we have a1 z over z minus 1/2. That's an exact structure in the table. We have a sub 2 z over z minus 1/4. That's an exact structure, and if you solve for that, you end up with 4 and minus 4. And you already could have anticipated where that's supposed to be. Question? So if you had something like, I think the question was, what if we had this? Then what you're doing is you are going to end up with z minus 1 over the z minus 1/2, z minus 1/4, and now you can solve for a1 and a2 using that expression. You'd multiply through by z minus 1/2 when you're trying to solve for a sub 1, replace z with 1/2, and you need to leave that z minus 1 in the numerator. I'm going to erase that because I don't want that in the notes, and that would really confuse people. But did that answer your question? So if you have something like that, then really all you're doing is you're wanting to preserve that initial z, and in this case that's going to be kind of not correct. We would want a higher power denominator in order to have that z minus 1 factor in the numerator. Questions on this? This was 2 real poles, but it came from a quadratic. You could have a quadratic that now gives rise to complex poles. In this case, if you plug this into your calculator or through the quadratic formula, you would have poles at z equal to 1/4 plus and minus j 3/4. And now we're saying the region of convergence C is beyond the square root of 0.625. And the way that, and now I do have one of those factors in the numerator. I not only have just a z, but I have a z minus 3/4. But what I want to do now is if I have complex, now I need to find, now I should be expecting a exponentially damped sine and cosine structure in the time domain. And if I just wanted the structure, you wouldn't have to solve for the partial fraction expansion coefficient. You could just say, oh, an arbitrary alpha 1 times an exponentially damped cosine. But from those exponentially damped sines and cosines, I want you to tell me what is the contraction or expansion, what's the r, what's the radius of that pole, and what's the angle of the cosine and sine to give me the frequency behavior in the sine and cosine, or how it's oscillating. And you can find that from these complex poles being at 1/4 plus and minus j 3/4. Meaning, if we want the radius, we just find the magnitude or the hypotenuse of the right triangle formed from, now we're seeing that we have in the z-plane poles at 1/4 plus and minus j 3/4. So there's 1/4, here's J 3/4, and here's minus J 3/4. And there are our poles. And you could now sketch the picture if you wanted to. You could say, oh, there, I need to find the hypotenuse of that right triangle with a real part of 1/4 and a vertical, an imaginary component of 3/4. And that now gives you a radial distance of almost 0.8. But that now tells you where it lives relative to the unit circle. And what's the region of convergence? If this y, capital Y of z converges for z, magnitude of z beyond the square root of 0.625, what's that telling me? So this is now equaling 0.7906. Now I have an unbounded region of convergence that's actually including the unit circle. I should have, even though it's bouncing back and forth because of a sine and cosine, it's damped, it's exponentially damped by this radius value of 0.79. And the angle that this is making, so this is now the radius r, and there's the angle theta sub d. And that angle is pretty big, it's 71.56 degrees. That's just the inverse tangent of 3/4 over 1/4. So that z is now some r at an angle theta sub d. And you can solve this many different ways. Let me just solve it using complex partial fraction expansion coefficients. So I now have just two factors, two poles, one in the first quadrant, another pole in the fourth quadrant, and they're located in polar form, r e to the j theta sub d and r e to the minus j theta sub d. And that I find by just setting the denominators equal to 0. To find K1, I now multiply. Is it clear that I've now put this y of z over z, and that's now equal to this, what's left over, which was z minus 3/4 over z minus r e to the j theta sub d, z minus r e to the minus j theta sub d. And what I want to do is make sure when you're doing this that you connect or put K1, not its conjugate, but K1 over the pole factor in the first quadrant. So that's now K1 is over the pole factor z minus r e to the j theta sub d. That's the pole in the first quadrant. If you don't do that, your signs are going to be messed up, and they're not going to be consistent. Now, to find K1, we multiply both sides through by the factor underneath K1, which is z minus r e to the j theta sub d, and hopefully then it's clear that in this red piece that I've now just canceled that particular factor. And I now evaluate this guy over here at the value of z that causes that factor that I just canceled to vanish, or when z is equal to r e to the j theta sub d. And that's what I've tried to do in this next line. I now have z minus 3/4 over z minus r e to the minus j theta sub d, all evaluated at the pole that caused that factor that I multiplied through to vanish, which is z equal to r e to the j theta sub d. If you've done something wrong, you may start seeing, I'm dividing by 0. Something's not right. Well, you shouldn't be dividing by 0 when you're solving for these partial fraction expansion coefficients, in this case K1. K1 is now r e to the j theta sub d, and we know what r is, and we know what theta sub d is. This will involve complex algebra, but it's doable. And what's downstairs? Euler is showing up, but we have r, and now we have basically 2 times the cosine. Actually, that's a sine piece, so that's going to give us some j's, but you don't necessarily have to keep track of all that. You're just now trying to find a complex number for k sub 1, and obviously that's going to give you generically a complex number. And if k1 is complex, then it has a magnitude and it has an angle in polar form. Once we've found k1, we don't have to find k1 star, that's just its conjugate, but once we found k1, we can immediately write down this expression for its inverse Ztransform. It's 2 times the magnitude of k1, r was the pole, its radius away from the origin, r to the n, cosine of theta sub d was the angle of that pole, and the angle of k sub 1 gives us this time shift, or a shift in the argument of the cosine. And if you're following along, you might want to put on your 2-year-old cap and say, why? Where did this come from? Why can we now immediately, if we know that we have this expression for capital Y of Z, and we have a complex K1 and its conjugate K1 star, why do we know that we end up with this expansion? Well, we know that the time domain is just the coefficient, the partial fraction coefficient, times the pole raised to the n. If it was real, that would be the pole 1/2 to the n. In this case, that pole is complex. It's in polar form. It's r e to the j theta sub d. But we also have its twin, which is k1 star times the other pole raised to the n. And now all we're going to do is some algebra with these complex quantities to show that little y of n, the time domain sequence for capital Y of Z, is as indicated in blue. But are we okay with this black formula for y of n? And on the exam, I'm not going to accept complex answers. They're just too complex. No, I want the answers to be real. So I want you to give me r's and thetas in exponentially damped sines and cosines. So you could write this down, that's fine, but I want you to go a step or two further to show me that you can believe, and it's okay also if you start with capital Y of Z and you compute K1, now you can immediately just write down little y of n. You don't have to rederive it, but I want you to use the correct form. What I'm doing now is just showing you, or trying to convince you, that yes, indeed, y of n is that blue formula if you have found k sub 1 and k sub 1 star. In general, you're going to have a k sub 1, a k sub 1 star, maybe a k sub 2, a k sub 2 star, maybe an A, maybe a B, where the A is on top of a real pole, the B is on top of another real pole, and you have all of these pieces. But it's no more complicated than that. You can only have real poles and complex poles. It's just you might have a bunch of them. But now they all just give you a particular mode. Is that clear? I'm just illustrating this for one set of complex pole pairs because it makes the explanation cleaner. But the analysis goes through exactly the same for multiple complex poles. If you have an R1 at an angle theta D1, an R2 at an angle theta D2, you just have exactly the same formula with R1 and theta D1, etc. plugged in. But this is just the pole raised to the n. scaled by the partial fraction coefficient. But remember, K1 is complex, so we can write that as a polar number. Its magnitude and an angle. So that's K1 e to the j angle of K1. And R e to the j theta sub d raised to a power, we can just use the power formula, or just the facts related to raising a quantity to a power. That's just r to the n times e to the j theta sub dn. And we can do its twin. K1 conjugate has exactly the same magnitude. Its angle is just its negative. And so now we can say, oh, that's minus j times the angle of K1. And that's corresponding now to r to the n with e to the minus j theta sub dn. We can now combine or factor out a common magnitude of K1. That's just a number. We can factor out the common r to the n. That's the radial distance that pole is away from the origin. And we can start to combine these complex exponentials. E to the j, theta sub dn plus an offset. So only one term in that quantity is a function of n, the other is a constant. But that should start looking familiar, what's in square brackets. That's e to the jx plus e to the minus jx. That's just 2 cosine of x, where x is a little bit more than just x, but it's now 2 cosine theta sub dn plus the angle of K1. And you solved for the angle of K1 when you were doing the partial fraction expansion. You should probably go through this a time or two so that you feel comfortable with this, but now do you see where that formula came from? The 2 pops out front. I have 2 times the absolute value or the magnitude of my complex number, K1, the radius of my pole raised to the nth power, so that's now just getting incremented as we sequence through in time, as n goes from 1 to 2 to 3, cosine of theta sub dn plus this offset of an angle k sub n, or k sub 1. Questions on that? Then we moved into discrete equivalents, where discrete equivalents we sort of had 2 different scenarios. The right-hand side did not involve some hold device preceding our analog system. That was scenario number 1, and we talked about numerical integration, and we talked about pole zero mapping. In scenario number 2, that's where we did have a hold device preceding our system that we were trying to find a discrete equivalent for. And how many numerical integration approaches did we talk about? We had 3 different ones. We had a forward, we had a backward, and we had a trapezoid. And how did those arise, or how can you start to think about forward, backward, trapezoid? Do you remember? Where did those come from? Those were just how we were approximating that sliver of area that we were adding on to the total area up to time y of n minus 1. And that additional sliver we could approximate either with a forward approximation, a backward approximation, or a trapezoidal approximation. That's where those came from. Now this zero order hold, I'm seeing that some people are getting hung up because we started with only doing that for transfer functions. But we can have this for a transform, or we could have it for a state space. State space was lecture 4.3. That we did not do live. That was pre-recorded. So maybe that's where the disconnect was. But that was lecture 4.3, the zero order hold of a state space system. So that's now a state space continuous time. You're wanting to go to a state space discrete time with a hold preceding the model. And in our case, we're just going to go ahead and approximate that hold as a zero order hold, which just means hold at level in between sample periods. If we do the transform approach of the zero order hold, that's now capital G of Z equaling or defined as 1 minus C to the minus 1 times the Z transform of G of S over S. And we should be able to use tables that contain capital F of S and F of Z in order to transform between G of S. We just now what? Insert one more pole at the origin, and then we look at the tables and try to find where is this G of S over S structure. Or we may have to do a partial fraction expansion on G of S over S to identify the unique terms in that transform table. Now, as if I couldn't make it more challenging, the state space approach, I talked about two different ways of doing that. The exact approach, which is being illustrated here, and a numerical approximation approach. The exact approach is when you're finding the system matrix in the discrete time setting, capital Phi, from the system matrix in the continuous time setting, capital A, and you want to find the matrix exponential of E to the A capital T. A is a matrix, capital T is a scalar. And you can't just raise every element of the matrix AT, or you can't just exponentiate the matrix AT. You have to, if you're doing it by hand, you probably are wanting to do this processing in the frequency domain. Find the inverse of this symbolic matrix, Si minus A, and then each of the terms in that matrix you would inverse Laplace transform. And maybe we'll go over a little example in a minute. And the input matrix, gamma, you have to use this matrix exponential, e to the a t, except now if I put that in the argument of an integral, maybe it's e to the a eta. B, you probably want to post-multiply by the input matrix. That will probably minimize the number of integrations you will have to perform. If e to the a eta is 2 by 2, and B is 2 by 1, their product will be a 2 by 1 matrix. So you would only have to integrate 2 terms instead of 4. If you did the multiplication of e to the a eta by B sooner rather than later. Suppose I give you this block diagram, and I say precede this with a zero order hold and find a zero order hold equivalent of a state space system based on this block diagram. And you had this on your cheat sheet. You go, He didn't give me an A matrix. Well, I did, but I didn't give it to you explicitly, did I? I'm giving it to you implicitly or indirectly. I'm giving you an A matrix and a B matrix. How do we create the continuous time system matrices from this all-integrator block diagram? The strategy is just to assign state variables as outputs of your integrators. Suppose that I now said, let me call this output of that integrator x sub 1, the output of that integrator x sub 2. What's the order of my system? I have two integrators. It's a second order system. I should be looking or expecting an A matrix that's 2 by 2. If the output of that rightmost integrator is x1, the input must be its derivative, x1 prime. If the output of the second or the leftmost integrator is x sub 2, then the input to that integrator must be x sub 2 prime. And now you should be able to populate the A, the B, the C. What's the D matrix? What's the matrix that directly connects the input U to the output Y? 0. There is no direct connection. There could have been, but there is not in this example. Maybe we do start with C, the output matrix. How much of x1 is added in to create y? How much linear combination of x1 is needed to build y? You see y is 2x1 and it has no x2. This output matrix is now 2, 0. Where y is supposed to be c times x1 of t, x sub 2 of t. So that a 1 by 2 output matrix C, when multiplied by the 2 by 1 state vector, will give me a scalar y of t that's just 2 x sub 1 of t. What's my B matrix? Well, what's the A matrix? I'm looking for, is there anything coming from x sub 1? So really x1 prime is the arrow coming out of that summing junction. It's built up by all the arrows coming in to that summing junction. Or let's start at the bottom and work our way clockwise. Do you see that we end up with minus 3 times x sub 1, making up x1 prime? Do we have any x sub 2's entering to make x1 prime? And we have x sub 2 unscaled, just coming in directly. So it's 1 times x1. What's that other arrow doing coming in? We've already accounted for x1 and x2, but there's another input to that summing junction. Well, that's feeding the input in with a gain of 6. So the top row of B, which impacts the definition of x1 prime, contains 6 U's. What about the second row of A and B? x2 prime is the arrow coming out, and it's built up from all the arrows coming in to that summing junction. There's only 2 arrows. We look for x1. Does that feed into x2 prime? Yes, with a gain of minus 4. Does x2 feed in to build up x2 prime, or the time rate of change of x sub 2? No, so there's a 0. We have one more input, and that's 5, that scales U. Questions on finding A, B, and C, and D. In this case, D is a 1 by 1 matrix that's 0, that's scalar. Pardon? What is D? D is in this equation where we had D U of t. D is the direct connection between the input and the output. And in our case, there was no direct input connection from the input to the output Y. And for that reason, then we could put it in there and just realize that capital D, the D matrix, is 0. And then U does not directly influence Y. That would allow us now to use the A and the B to find phi and gamma and H and J, the output equation. In this case, H would be C and J would be D. If we have Y of n is now C x of n plus D U of n, that's the same as H x of n plus J U of n, which is like homework problem 5, sort of, but that was doing it from not the zero order hold equivalent, that was doing it as a numerical integration approach. But not only can we do it with exact expressions for phi and gamma, we can also numerically compute phi and gamma, and in practice, that's probably what you would do. You probably, if you had a fifth order system, you probably wouldn't want to be symbolically inverting a 5 by 5 Si minus A matrix and inverse Laplace transforming 25 expressions. You would probably say, forget that, let me start with an A matrix. I have that, that's minus 3, 1, minus 4, 0, that's 2 by 2. A B matrix, oh, I have expressions for that that will converge rather quickly if I just do this preliminary computation on another matrix, psi, where psi is sort of this nested collection of ATs. It's AT over 2 times I plus AT over 3 times I plus AT over 4 times, and you can stop me when you get tired. But probably if you go up to 5, that's probably enough to be accurate enough for this class. You could go to 4 and it's probably accurate enough. And here I tried to do it in colors to emphasize the nested behavior of that numerical computation. But once you have capital psi, now it's a fairly quick numerical computation to find capital phi, which is the system matrix for the discrete time representation. Phi is just I plus A, that's the original continuous time A. Capital T is not a matrix, that's a scalar, so that's easy to do. And psi you just determined in the bottom row. And psi was dependent on the original system matrix A for the continuous time system. So once you had that system matrix, and how would you pick capital T? What's capital T? Let's say somebody gives you this A, B, C, and D, and they say, numerically find phi and gamma. Or maybe they say, do the exact determination of phi and gamma. How do you find capital T? Pardon? You need a sampling frequency. You just grab one out of midair. How do you pick that sampling frequency? So on the exam, If you're completely lost, you could say, I need a sampling frequency, and I know my sampling frequency relationship. I know omega sub s is 2 pi f sub s, and that's 2 pi over capital T. And you could say, find T from that. You won't get all the points, but at least I know, well, he or she remembers the formula. How to connect T to the sampling frequency. But how do you find omega sub s? If you're given A, B, C, and D, if you have this alphabet of a system, which is the continuous time system, how do you find omega sub s? And let's assume that we're not going to change the dynamic behavior with our controller or the bandwidth or the speed of the system. We're not going to modify that with the controller, so I'm just going to say I'm happy with A, B, C, and D's dynamics. I want you to preserve that with this discrete equivalent. How do you find omega sub s, which is really a way of finding capital T? You need capital T to do any of these numerical computations. And if THARP doesn't give it to you, now what do? Question or answer? So now you use the eigenvalues. Which eigenvalues do you use? Does B have any eigenvalues? Not in general. If you have one input, B's not even square, so you can't talk about eigenvalues of B. Where are the dynamics in your system? In the A matrix, in the system matrix. So you would go to your continuous time system matrix A, and you would find its eigenvalues. And now what do? Suppose you have an eigenvalue of A at -2, and you have another eigenvalue of A at -5. So let me say that we have lambda of A equaling -2 and -5. Well, I have omega sub s, and now you're giving me negative numbers. What are you doing to me? Now what do we do? Those are associated with poles in our system, correct? We have a pole at -2 and we have a pole at -5. And somebody asked in the quiz, which of these poles dominates the behavior? So now I'm going to really confuse you because I'm mixing apples and oranges. Which one dominates the response? The pole at -5 or the pole at -2? And when dominates, I'm basically meaning which one's the slowest, which dominates the behavior. The fastest one's going to happen, and then the slow one's going to dominate. That's the one you're going to see mostly. Which of these corresponds to what modes? This gives rise to an e to the -2t and an e to the -5t mode behavior. Which of those is the slowest? Which decays the slowest? You could just plug in two numbers and say which one is going to give me the slower response. Is it clear that -2, the mode at -2 is the slowest? That's the dominant, but that's not the one you use to find the sampling frequency. That's why I said I'm now going to confuse you. You want the fastest one to determine how fast to sample. The pole furthest away from the origin in the S-plane is the one that you would pick. So now you would use the pole at -5 to determine, well, let me just say this. Let me say omega sub s is going to be connected to the magnitude of the distance away of your fastest pole from the origin in the S-plane. Omega sub s is now 5. Now that you have omega sub s is equal to, wake me up. Wake me up. This is the natural frequency of the system, not your sampling frequency. This is your system's behavior. What do we do relating the natural frequency of your system to the sampling frequency? This is the rule of thumb. They're related by 30. You want to sample 30 times this speed. meaning omega sub s is now 30 times omega sub n, or that's this 150. So that you now set that equal to this and solve for capital T. Capital T is now 2 pi over 150. Is that clear? And now you can do this numerically. You have A, you have psi, you have B, you now have T from the eigenvalues of A. Yes? So now if I have a fancy computer that's going to sample really, really fast, you may want to actually sort of downsample so that you're not basically just picking up noise, or you may sample really fast and average those samples and say, I really just need to be sampling at 100 milliseconds or 0.1 seconds instead of 1,000. So you may want to be throwing things away even. But the reason why you might want to throw things away is because your A matrix and your B may not have much structure if you're sampling really, really fast. Everything's going to be clustered right around z equal 1. And maybe you don't want that. So you may run into issues with rounding also, and we're not really talking about that in this class. So we're, right now, at this point, we're just worrying about sort of the fundamentals. But you have to worry about rounding, you have to worry about how fast do I sample. But at this case, most of our control sampling in today's technology doesn't seem very fast for our systems that we're playing with. So that's how you could numerically find a zero-order hold. Now for numerical integration, which is scenario number 1, now we do not have a zero-order hold preceding this system in the continuous time that we're trying to find an equivalent for. We could do the forward, backward, and tungsten, or the trapezoidal. That's referred to many different ways. And you could think of the trapezoidal as being an average of the forward and the backward if you put that 2 underneath the z plus 1 in the denominator. And we've derived, and you've derived on homework number 4, problem 5, a backward state space formula, and I gave you the tables for the forward and the trapezoidal to come up with a way to do discrete equivalents for a given A, B, C, and D in the continuous time setting or system. And in this case, it's fairly straightforward. If you have a second order system, if you have an S squared, you replace that S with one of these formulas in Z and square it. You have a cubic. You take that expression, Z minus 1 over TZ, and you would cube it. And if you had a square in there, you would square it, so that you now have these squares and cubes of Z's floating around. Pole zero mapping, we talked about that a lot today in the previous lecture, but a lot hinges on the pole zero excess. But what do you do with the pole zero excess? That gives rise to these Z plus 1 factors. You're going to match poles and zeros from this. Using that relationship, your pole zero excess will give rise to so many Z plus 1 factors, and if you're not worried about the delay between your input and the output, you have as many Z plus 1 factors as you have pole zero excess, or more poles than zeros. So if you have a pole zero excess of 3, you're going to have s plus 1 cubed in the numerator. And then you match gains. And there what you may want to start looking at is, where is my gain bounded in my expression for g of s? Is it bounded for low frequencies? When s is equal to 0, that's as low as you can get. Then you might match DC gains. And if you match it DC in the S domain is s equals 0. Because of this relationship of z is equal to e to the st, when s is equal to 0, z is equal to 1. And so you can now match or replace z with 1 when you're replacing s with 0 and you're setting those two expressions equal to each other. Question? So now the question was, if I give you a transfer function, am I going to give you that much of a hint and say it's low pass or high pass? Maybe not. So you may want to look at that transfer function and say, is this well behaved at low frequencies? If it is, meaning if you had a pole at the origin, is it well behaved at 0? If you had a transfer function that looked like g of s is equal to 1 over s. What happens at DC? What happens at low frequencies? What is this system? That's an integrator, isn't it? What happens at DC? If you try to plug in s equal to 0 to that, what's going to happen? It's going to go unbounded. If you have a lot of gain at DC, do you not? With an integrator, it's trying to, if you give it a constant, it just sits there and integrates that constant up. So you maybe can't use DC or matching at DC. What about at infinity? At high frequencies, if you let s march off to infinity, what happens here? Gain vanishes. 0 equals 0. Yeah, that's true, but it doesn't help me find a k, does it? Now what? Well, maybe you pick a convenient value of s and go with that. Meaning, a convenient value for s, you might say something like, oh, g of s with s equal to j1. And then you find the magnitude of this, and that's now the magnitude of 1 over j1. What's the magnitude of that? Where are you in the complex plane in the denominator? j1. If you looked at the complex plane, you would just be at j on the vertical axis. What's the distance that is away from the origin? 1. So this now has a gain of 1 at omega equal to 1. But then you can't just be arbitrary on z. Now you would have to be consistent with g of z. This is getting really messy, but this is now g of z at z equal to e to the j1 times t, because we've replaced s with j1, whatever t is, and now you would find the magnitude of this complex number and set that equal to 1. Do you see why we've been focusing on DC and infinite when things are well behaved at infinity or DC? It gets kind of messy when it's not. But you have the tools to do it. So now if the gain at DC was 0, and what's the, now we're seeing that if we had this, maybe we had more of a high pass behavior. At low frequencies, the gain is 0, but it has a bounded gain at high frequencies. This is now more of a high pass behavior for our transfer function g of s. So this is with s equal j omega. Then we would match at infinity, which says we would let s march off to infinity in g of s. We should get a bounded number, and we'll set that equal to g of z when z is at its infinity, which is z equal to minus 1. And if I give you something like this, now what? That's a band pass. But you could say, oh, I'm going to match right here at star. And then you just, that star might be s equal to j 6.725. Who knows? Maybe that frequency was 6.725. You now replace that with s equal j in g of s, and you map that through the z equal to e to the st. I don't think it's going to get that involved on the test, but I'm just trying to let you know that you have the tools given the time to do that. I just gave the answer. But on this, if I said do a pole zero mapping for this transfer function, where are your poles? They're at minus 1/2 plus and minus j 1/4. They're complex, so you'd have to map complex poles. Do you have any finite zeros? No. Do you have any infinite zeros? What's your pole zero excess? You have 2. So now you would say, oh, I have 2 zeros at infinity. So that gives rise to this z plus 1 quantity squared. My structure downstairs, I know I'm going to have 2 poles. They're going to be complex. But if I just arbitrarily put in some coefficients, I know that they will be an alpha 1 and an alpha 2, and I have some gain k bar. But in g of s, is that low pass, high pass, or neither? What frequencies would you match in this transfer function for g of s? What kind of a shape does that have? At low frequencies, is it bounded? And when I say that, you might just look at an extreme and say, what's s equals 0 give me? Well, that gives me a numerical value of 4 over 1/2 squared plus 1/4 squared. So this is low pass in nature. It's flat, and then it starts rolling off. So this is low pass. And you would match things at s equals 0 and g of z equal to 1. But now if I wanted to implement this with an output u and an input e, you see what I would have? This z plus 1 squared gives me a z squared plus 2z plus 1. It's second order, so I'm multiplying top and bottom by z to the minus 1 to give me everything in negative z powers, which now allows me to start writing my difference equation that includes a u to the n minus 1 and a u to the n minus 2. And upstairs I have a e to the n at n, e to the n minus 1, and an e to the n minus 2 with some kind of coefficients. And today we talked about what if we didn't like having to use that input now. Then what would we do? We would decrease our zeros at infinity by 1. So we did have 2 zeros at infinity mapped to z plus 1 factors. Let's remove one of those. Let's just raise it to the 1 power. And then I think you would see, or you can see, that our numerator now just contains an e to the, or a z to the minus 1 and a z to the minus 2. And that gives rise to an e to the n minus 1 and an e to the n minus 2, and I've now lost my input e at the current time, which is what I was maybe trying to accomplish. Are there questions on this? Yes. So how do we know which one to do? Which of these pole zero mapping do we use? I would default to the first one, the one that I taught you, and not the one that corresponds to MATLAB. But I was just today trying to let you understand why MATLAB might be giving you the answer that it's giving you. Unless I say something to the effect of, make sure there's at least one sample period delay between the input and the output. Then your hair on the top of your head starts to stand up and you go, something's different here. Oh, I have to not map all of these zeros at infinity to these z plus 1 factors. Let me reduce that by 1. Then you would use the second approach. I'm trying to make you more well-rounded. I'm not trying to confuse you. Really, I'm not. But I want you to understand what's going on, or what can be done. I'm fine with that and finishing if you're okay. If there are no more questions, I will shut it down. Good luck.